Let's figure out the moment of inertia of a thin circular ring. So we are considering the ring to be uniform of mass m. So the mass distribution is uniform. So the total mass is m and the radius is r. It's rotating about an axis that passes through its center and is perpendicular to its plane. So basically, if I happen to consider a ring in this manner, this being the center, this would be of radius r, and what else? This is the plane, maybe xy plane, whatever you want to consider. Point is, the axis of rotation is perpendicular to this. Okay, so let me actually do it properly. It would be perpendicular in this manner. That would be your axis of rotation. It's important for us to understand where the axis of rotation is. And how it is. So this is making an angle of, it's obtaining an angle of 90 degree. This is the case. So we had to figure out the moment of inertia with respect to this axis. So we have a thin loop and all the mass elements dm will be at the same distance r. So first thing first, so we have I is equal to r square into dm. First we look at r, because see, end of it, this is the formula that we'll use. We look at r. So how do I write it? R. That's the heading. So because the ring is thin, all mass element dm are at the same distance. What is the distance? Yes, r. Okay. Then we have dm itself. So how much is dm? We need to express in terms of m. So dm will be equal to mass of a small element, that is m divided by 2 pi r into dx. So this is nothing but your density times the length. So let me make it clear. dm is the mass of a small length of ring, small length dx of the ring. So basically we have dm is equal to density times dl, guys. I hope you guys know all of this formula. So it's nothing but density is given by the entire length divided by, entire mass divided by entire length. Entire length in this case is 2 pi r into dx. Your small length is density times of length actually. Any mass is density times of length, and mass in this case is dm. Density is m by 2 pi r into length is dx. Now let's substitute all of this into I. Substituting dm and r value into I. So I is equal to integration of r square m by 2 pi r dx. So r and r will get cancelled. Since r is constant, we have 2 pi, m is also constant. We just have integration of dx. Now, integration of dx, let me put it to you guys in this way. Say you have a ring, right? And we consider small length dx. So imagine that the length is, basically its length. So I can put it across in this manner. So one end of the length, if it starts from 0, the other end will go to 2 pi r. Now, what will be the limit? So this is dx, remember? This is dx. So I need to add the effect of all of them. So what should I do? I should add up from one end to the other end. So I'm integrating from 0 to 2 pi r. Okay, I'm integrating from 0 to 2 pi r. Does it make sense? So from one end to the other end, we need to add all of them. So I'm integrating from 0 to 2 pi r. So we have r by 2 pi m, and integration of dx is x, 0 to 2 pi r. And when I do integrate all of this, I'll end up with rm 2 pi r minus 0. Actually, all of this this step can be skipped, honestly. So 2 pi r gets cancelled, and we have mr square. Okay, so this is when we have the axis of rotation over here. What if I shift this axis of rotation to the extreme? So let's start with case. Case when the axis of rotation is tangential and perpendicular to the plane. So basically what I'm showing is this, and we have this. So we can name this as AB and this as PQ. So this is our new axis of rotation. And this has a distance of clearly r, right? So how do you do it? Using correct parallel axis theorem. So as per the parallel axis theorem, the inertia along PQ will be the inertia along the center of mass, which is nothing but your AB, plus the total mass of the object and the distance covered. And distance, it has got displaced. The axis has got displaced here. D is equal to R. And M is M. And we just found this. So this is mr square. Obviously, this has to increase into m into r square. So this is nothing but, it's a simple straightforward 2mr square. Actually, let me finish it up here itself. 2 times of mr square. It has to increase, and it is doubled actually. Now let's look at a case wherein you have moment of inertia of the ring along any diameter. So basically, okay, I have to copy this actually. So diameter is nothing but this is a diameter. This is a diameter, right? So what we are doing is here we are actually, sorry, let me discuss this. So we are say rotating over here. We are rotating over here. In this case, we are rotating over here. Clockwise, anti-clockwise will not matter. So for this, what should I use? Yes, we can make use of using perpendicular axis theorem. Now, what does perpendicular axis theorem tell? So if I name this as say AB and this as PQ and this as A dash B dash, the perpendicular axis theorem tells that if I figure out the inertia along AB, add that with A dash B dash, this should give us moment of inertia along PQ. But moment of inertia of AB is equal to moment of inertia along A dash B dash, as both are case of rotating along a diameter. So I'll call this as AB itself, both are AB. So 2 times of AB is equal to, along PQ we already know it is MI square, sorry, MR square. And so along the diameter, it's a bit easier to rotate. It's half of the energy taken to rotate along the plane and through the center of mass. And that's that. Now, finally, I have the case wherein we have moment of inertia of the ring. Then this would be parallel to diameter and tangential. So basically, let's see if I can use this. I can kind of, space is what I don't have. Okay, manageable. So basically what we're looking at, say we have a diameter in this manner and we have a tangent. So let me try to draw one tangent. Remember, these two are parallel to each other. Oh, I can't. I have to do something like that. It would be so, and this is parallel to this. This is tangential. Then we have AB, and then we have A dash B dash. So that's that. So this is the case. So basically we are rotating in this manner. So imagine that it is in this manner. So this will, if I rotate it very fast, it will form a donut shape. It will be a, no. Almost a donut shape. I mean, it's almost closed actually. Almost closed. But anyways, this is the case. So what can I use? Using correct parallel axis theorem. I kept this as capital letter. Let me continue to do so. So parallel axis theorem. So we have along AB moment of inertia will be equal to moment of inertia along A dash B dash plus md square. Here d is what? Here the distance that the axis has moved is r, and we have half of mr square plus mass is m r square. So this is 3 by 2 mr square. So as you can see, you don't have to remember everything. If you remember or if you understand this derivation, actually the main derivation, which is also quite simple, you will be able to derive the other formulas out. Of course, get used to the idea of deriving and then you can memorize. In time, you have to memorize for your competitive exams. That's there. That's the sad part. But yeah, first thing is try to understand how to derive, and then derive. So it's all have to do with all we have to do is consider small part dx. Imagine that it's a line. It is a line of length 2 pi r, and then you need to integrate from one end to other end. So when you integrate, you add up every part of it and you end up with the formula. So please write this heading and copy everything.